All right, I think it's about time to get it going. Welcome back, everybody. I hope everybody can hear me. I'm sorry that the class had to end up the way it did. We fortunately, I was running a little bit ahead on the material going into the last week, and my what I had planned on doing covering this week was two topics which are kind of well, um,
Brian left during my presentation.
can you guys mute yourselves? I don't know what happened. I had two topics to do this week that were kind of optional. They weren't, we didn't absolutely have to do them. So we're just not going to do them. Then it worked out okay, I guess. That means that today all I really want to do is talk about the final exam. But I actually had one thing to say, which is not really a topic all by itself, but this is definitely important material, you might say. I mean, it is material. Just could you give me like 10 minutes to say one thing that's important, although it's mostly just a matter of terminology or notation. So let's talk new stuff, I guess, for 10 minutes or so, and then we will do some review for the test. What I would like to discuss is called the indefinite integral. The indefinite integral. Let's do it. The indefinite integral. I hope you recall the definite integral is that thing with the two numbers, and you evaluate it either by doing the Riemann sums or by using the fundamental theorem of calculus. Usually, you don't want to use the Riemann sums. That's called the definite integral. There's another thing called the indefinite integral. Sorry, this is messy handwriting. The indefinite integral. If you recall, the fundamental theorem of calculus number 1, this was the weird one. It said the derivative dx of the integral from a to x of f of t dt is equal to f of x f of x. That's it, right? I was about to say dx, but it's not. It's f of x. All right. When you look at that, the one sort of very simple way of seeing this is it looks like the derivative cancels the integral sign, right? That's kind of what it looks like here. On the left, I have the derivative followed by the integral sign, and on the right, I have basically just what was on the inside there. It's almost as if the derivative is canceling the integral sign. This is not a totally wrong idea. And another way of saying that is you could look on both sides of this equation here on both sides. It says the derivative of this equals this. Another way of saying that is that this is an antiderivative of this. So I will say more correctly or more specifically, f of x, the right-hand side up there, is an antiderivative of that integral. Sorry, the other way around. This integral is an antiderivative of this because the derivative of the integral is the f of x. So specifically f of x, sorry, I meant to start with the integral here. I'm still kind of in a daze from the COVID. The integral a to x of f of t dt is an antiderivative of f of x. All right, that's because the derivative of this integral is f of x, which means the integral itself is an antiderivative of f of x. All right. And so this is why it is it's sort of a a typical parlance that when people see the integral sign, first of all, it does mean the area under the curve, but also the integral sign has the connotation of an antiderivative. And so we use the integral sign also we use this to denote the general antiderivative. So that right there, I wrote an integral sign with no little numbers in it, all right? Just the integral sign with no two little numbers. This does not represent the area of anything. It's something that, like, conceptually completely different. It means the antiderivative of that function on the inside. And the dx here really means nothing at all. You could, in a definite integral, you can imagine the dx represents some kind of small width of the tiny little bitty rectangles. But in this kind of a thing, this just means the antiderivative. It denotes the general antiderivative of f of x. And this is called the indefinite integral. The indefinite integral, right? It's a function. So these things are very different. This, a to b, f of x dx, this is called the definite integral. When you see the little numbers, that's the definite integral. The definite integral. And what it means is it represents the area under the curve on the interval a to b, right? And it's a number because it's an area. So that thing, when you write an integral like that, you can evaluate it. And I mean, if you're able to evaluate it, the answer is a number. That's called the definite integral. Whereas if I just write this with no little numbers, that's called the indefinite integral. The indefinite integral, and it is the antiderivative. It's totally different from the definite integral, which represents an area. The indefinite integral is an antiderivative, and it's not a number, it's a function, right? It's a function with a plus c in it. So it's not even really technically a specific function. It's a function which has some undetermined constant as part of it. All right. So this is the definite integral versus the indefinite integral. This is the last thing that I wanted to say, which is really just a matter of notation. But it means that for example, if I say, like, what is the integral of x cubed minus 7x squared plus 5 dx, that's the antiderivative of that function. That's what it means when I write the integral sign with no little numbers. It just means the antiderivative. And what is the antiderivative of that? It's whatever you do, the usual thing with the constants, with the coefficients. 1/4 x to the 4 minus 7 times 1/3 x cubed plus 5x plus c. The indefinite integral is the antiderivative with the plus c in it. All right, that was my 10 minutes. I said I had 10 minutes. I was gonna, squeeze this in before I talked about one of those other topics, but we didn't get to them. But it's important. I hope everybody knows what the integral sign means without the little two numbers. That's called the indefinite integral, and it just means the antiderivative. Now, I said that we were going to have another homework assignment. That's because I thought we were going to do more new stuff this week. Since we just didn't do any of that new stuff this week, that means there will not be another homework assignment. I hope you weren't counting on this. No more homework. The only thing that I want to do for the rest of our time, today, is just talk about the final exam. So I will refresh our memories. First of all, the exam is a week from today. Friday, December 17 at 3 p.m. in our normal classroom. The final exam, just like all scheduled exams, are scheduled for 3 hours. So we'll have from 3 to 6. I'm not going to write the test I'm not going to, pitch it so that it's going to take you 3 hours, but you can have the whole 3 hours to do it. It'll probably take you less than that, but you can take the 3 hours if you want. It's going to be, same format as our other tests. I hope that everybody knows more or less what to expect from the exam. I am about an hour ago, maybe half hour ago, I emailed out the review sheet to everyone. I'm going to also put it in the Zoom chat right now, just so that you'll have it on hand. Sorry, I gotta find it here. All right, you should gotten it in the Zoom chat, or hopefully you already had it. What you'll see in the review sheet is, first of all, I just attached, or I sort of pasted in all of the review questions. Sorry, I'm looking at the wrong one on my computer. I pasted in all of the review questions from the earlier exams, our first 2 tests, and then give me a moment here, sorry. Okay, we have the older ones, and then if you go to page 5 in the PDF, you will see the beginning of the new stuff. It says the new stuff covers at least 1/3 of the exam. This is the stuff that we've had since exam number 2, starting with Newton's method and then going through to the end, really. Maybe we could just look together about the list of formulas. So I'm going to give you some formulas on the test, and I'm going to have some that I would expect you to remember, just because I'm not big on making people memorize a whole lot of formulas. So if you're looking in the PDF that I sent on page 6, you can see my list of formulas that you should remember. You should know the SOHCAHTOA thing, and you should know sines and cosines of special angles. This is just like on the other tests. You should know what the other trig functions are, the secant, cosecant, those kinds of things. You should know the basic derivative rules, which is the power rule, product rule, the quotient rule, the chain rule. Derivatives of sine and cosine, and antiderivatives of sines and cosines. You should know basic geometry formulas for doing like related rates and optimization problems. Here's a new one. You should know the definite integral formula as a Riemann sum. You see I wrote it down there. The integral from a to b of f of x dx is the limit n goes to infinity. The sum I equals 1 to n, f of xi times delta x. And you have to know that the delta x is b minus a over n, and the xi is a plus I times delta x. And then you have to know those 2 summation formulas, the sum of 1 and the sum of I. And then I'm going to give you these other formulas. So I'm just going to write these down at the top of the test with no context. But that first one there, you might want to, you should definitely know like what these are. The first one there is the definition of the derivative, in case I ask you to find a derivative using the definition of the derivative. That's like the long way of doing it. You may be called upon to do that on the test, so that's the formula for that. The second one there is the linear approximation formula, which is a little bit obscure, and I didn't want to make you have to worry about memorizing. The next one is the Newton's method formula, which also I figured I'd give you a break and give you that formula. And then the last 2 summation formulas, which I told you all along I would tell you. All right. I think that's it for the formulas. I don't know if you feel like I left any out. Anybody unsure about, do I need to know this or that? Please let me know. I tried to think of everything. Otherwise, that's all that I had to say for today. I'm still, like I said, I'm still kind of in a daze from the Rona, but hopefully I'll get better soon. So we can talk, we got plenty of time. I would be happy to go over any examples about anything that anybody wants to talk about. If you have particular questions, you can shout them out or put them in the chat. I would be happy to talk about whatever you all want to discuss. I did get... Oh, go ahead.
Can you, for Newton's method, can you go over just how to create f of x?
Yes, yeah, that's a good question. Let's try a Newton's method example. Finding the, deciding what the f of x should be, yeah. Newton's method, Newt's meth. To find the f of x, the point of Newton's method is it finds values, finds x where f of x equals 0. So if I ask you to estimate the particular, a certain number, like the typical question is estimate the square root of, of 10 or something like that. You have to invent a function for which that number makes it equal to 0. So something like estimate, what if I said something like the square root of 17? You have to invent a function. You need to build f of x with f of 17 equals 0. And the way f of the square root 17 equals 0, right? The typical way to do that would be if it's a square root, you use x squared minus whatever that number is, because this is a function where if I were to plug in square root of 17 here, it would become, the square root of 17 gets squared, and then it becomes 17 here, minus 17 would be 0, right? So for a square root, you use just that. If I had some other kind of root, a cubed root or something like that, if it was, the cube root of 30, then I would use f of x equals x cubed minus 30, right? You always use this, whatever that thing is, you use that power of x, and then you go minus whatever the number inside there is. Or this is the basic idea. I mean, those are really the only kinds of numbers that you should expect me to ask you to find using Newton's method.
Thank you.
All right. I had a request by email. Somebody wanted to make sure I did an example of evaluating a definite integral using the Riemann sums. That's one of the most sort of in-depth, I think, I don't know about hardest things we've done all semester, but it's certainly a problem that will take you quite some time to do, and there's lots of chance to mess it up. So let's try one like that. Let's try an integral, evaluating an integral using Riemann sum. Actually, let's do it the easy way first. The easy way is using the fundamental theorem of calculus, and then we'll do the Riemann sum. We'll do the easy way first so that we can check our answer. How about the integral from 0 to 3 of 2x plus x squared? Let's try that. So first of all, this is part A, using fundamental theorem of calculus. This is the easy way. We do the antiderivative. It becomes 2 times 1/2 x squared. That's the 2x, and then plus 1/3 x cubed. That's the x squared, and I plug in 3 and 0. This 2 times 1/2 x squared, that's just the same as x squared, isn't it? Would you mind if I did that? It's just x squared. Plug in the 3. I got 3 squared plus 1/3 times 3 cubed, minus, plug in the 0. 0 squared plus 1/3 times 0 cubed. This is 0 over there. So this is just 9 plus, Isn't that 9 again? 18. All right? I think that's right. Okay, so that was the easy way. Let's do it now the Riemann sums way. Hopefully we get the answer to be 18. We'll try it out, see what happens. All right, so part B is going to be the Riemann sum. Riemann with 2 N's. All right, you should never do it this way unless I tell you to do it this way, because this is the hard way. To do this as a Riemann sum, you should figure out what the delta x is, first of all. Delta x is always, this you just have to remember, b minus a over n, where b and the a are the interval endpoints. So 3 minus 0 over n, this is 3 over n. And the xi is a plus I delta x. Sorry, I have convulsive yawning. I don't know why, but compulsive, not convulsive. I've been yawning a lot. The COVID. The a in this case is 0, which is good. That will simplify things. I delta x is just I times 3 over n. So this I would write 3i over n. All right, let's plug this business in to the Riemann sum formula. So this formula also you'll need to remember. It's lim n goes to infinity, the sum I equals 1 to n, f of xi times delta x. So we do it. The sum I equal 1 to n. All right, f of xi is, I scrolled it. It's this function here. Don't do the antiderivative or anything. You just use this, direct this function exactly as it is. 2x plus x squared. And I have to plug in xi, which is 3i over n. So it's going to say 2 times 3i over n plus 3i over n squared. I plugged in, instead of x, I plugged in 3i over n. That's just f of xi. And then all of that times delta x, which is 3 over n. All right. So this here was, this was f of xi, and then this part right there was delta x, right? I had to plug in f of xi times delta x. Okay, now it's just a matter of expanding everything and simplifying, and hopefully we're not going to screw it up. That's all we do from now on. Sum I equal 1 to n. Okay, let's do multiplying by 2 and squaring. So this becomes 2 times 3i over n. I'll write 6i over n plus square it. This is going to be 9i squared over n squared. All of this times 3 over n. Now let's distribute that. 3 over n. Sum I equal 1 to n. Distribute 3 over n, 18i over n squared plus 27i squared over n cubed. All right. Okay, continue. Now we should split up the sum and factor out everything except for the i's. So it's going to be split up the sum and factor out 18 over n squared, the sum of I, plus 27 over n cubed, the sum of I squared. All right, I split up the sum into 2 sums. And then in each sum, we factor the constant out, factor the n's out, and all that remains inside is the stuff with the i's. And now we use the formulas for the sums of the i's. The first one there you need to remember. The sum of I is n times n plus 1 over 2. And the second one there, you should look on the paper that I'm going to give you, or you can remember it. It's n times n plus 1 times 2n plus 1 over 6. And finally, we take the limit, and I hope we're going to get 18. Remember, that's supposed to be the answer. When I take this limit, these n's will all cancel. I have n squareds on top with a coefficient of 18, and on the bottom I have n squareds with a 2. So this is just going to give me 18 over 2. And then over here, I have n cubes on the top with a 27 and a 2, and n cubes on the bottom with a 6. So this one will give me 27 times 2 over 6. This is 9. That would be 27 over 3, which is also 9. So this is 18. I think I did it. All right, so that's a typical example of doing the Riemann sum. It's a lot of work, not especially hard. I don't know. There's just a lot of little steps where it's easy to mess it up. Fairly mechanical, though. What else shall we discuss? I'm ready for anything, especially a nap. Somebody says, can we do an optimization problem? Yeah, all right. I was afraid someone would say that. These are kind of difficult to come up with on the fly. Actually, I have my book here. Maybe I'll just look in my book for an optimization problem. There was an optimization problem on the last test, of course, which ended up being a bit of a mess for some people. It's hard to look at these and tell if they're going to be easy to do or a real pain to do. All right, I'm going to see if we can do one of these. The farmer with the fence kind of thing. Let's try. I believe this was not one of your homework problems. I don't want to repeat those. It says a farmer wants to fence in a rectangular plot of land adjacent to the north wall of the barn. And the fencing. Okay, so here's the setup. Like here's the barn down here. And the fencing along the west side is shared with the neighbor who will split the cost of that portion of the fence. So the fence goes like this. It's a rectangular area of fencing, and part of it goes along the barn, so you don't have to fence in that part. And this part, the left side here, is only half price. That's the idea. All right. The other two sides, they have to pay full price. This is half price because that's along the neighbor's property line. All right. And it says the fence costs $20 per foot. And the farmer has $5,000. And the question is, what's the biggest area that you can enclose in the fence here? What's the maximum area we can enclose? All right. This is the setup. I hope that makes sense. Sorry, it took me a while to settle down on this problem. All right. So we should begin by thinking about the function which is meant to be maximized, right? And write that in terms of a single variable. So first of all, the function which I'm trying to maximize or minimize would be the area of this fenced-in region, the red zone there. And it's going to be rectangular. We should maybe give some variables to the sides of the rectangle. I'll call this top side x and this one y, just because x goes horizontally and y goes vertically, all right? And the area of those two things is what I care about. And of course, the area equals x times y. The interesting thing to do at the beginning here is to write the area in terms of a single variable, like only x or maybe only y. So I'm going to redraw this again here. We have x and y like that, all right? There's actually no fence on the bottom, and the one on the left only costs half price. That's the rule for this. So we usually need another equation here which relates the x and the y. And in this case, it has to do with the money, right? This business here you can use to write down another formula. The fencing costs $20 per foot, and we have $5,000 to work with. So I'm going to make another equation here, which is that the total cost is going to equal $5,000. And what is the total cost? Well, the fencing that I have to build is x and y and another length of x. So I have two lengths of x plus one length of y. And it said each one costs $20 per foot. So I'm going to say it's basically like 20x plus 20y plus 20x again adds up to 5,000. But the x on the left is half price, which means that one is only going to be 10. All right. So what I did here is the price of each foot. You know, the x is how many feet this one is. Then how many feet the y is 20y, and then plus another $20 for these x's. This one's a 10 because the part on the left side is half price. All right. I hope the numbers are going to work out nicely for us, although I'm not quite sure if they are or not. Let's just simplify a little bit. You can add together the x's. This says 30x plus 20y equals 5,000. And I intend to plug in up here for x, y. I want to write that in terms of only one variable, not two. So I'm going to, let's solve this either for x or for y. I'll solve it for y. So I would say 20y equals 5,000 minus 30x, and then divide by the 20. Y equals 5,000 divided by 20 would be 250 minus 30 divided by 20 is 3/2. All right. I think I'm doing all right. Anybody, any questions so far? This is the y in terms of x. And so I can write my equation for the area is x times y, which is x times this stuff, 250 minus 3/2 x. And this distribute, just because I'm going to take the derivative, so I'm going to distribute this. It'll be a lot easier. Minus 3/2 x squared. All right. I think the numbers are going to work out nicely here, actually. Okay, this is my equation for the area in terms of a single variable. Now, to get the optimization problem means I want to find the maximum possible area. That's what the question was. So I need to find the interval of allowable x values here. The interval I'm going to get using this formula here. 30x plus 20y equals 5,000. If we, so the smallest the x could be would be 0, and the biggest the x could be would be whatever makes the y being 0, which would be, I guess, 5,000 divided by 30. So I will say the smallest x is x equals 0. The biggest x is when y equals 0, which would be, if I go up here, if I look right there and let y be 0, it will say 30x equals 5,000. And then we can solve for x as 5,000 over 30, which is 500 over 3, I guess. Whatever that is. All right. But in either case, the area will be 0 in both of those cases. In the first case, the area is 0 because x is 0. And in the second case, the area is 0 because y is 0. So area of x is 0 for both of these, which means that the maximum, I wrote these is, it's another COVID symptom. The area is 0 for both of those numbers, and so that means the maximum area actually will occur at the critical number. That is when the derivative is 0. So the critical numbers, there might be more than one. A prime, I'm going to take the derivative of that thing that you see at the top of the screen, 250 minus 3x. And then I'm going to set that equal to 0 and solve for x. A prime equals 0. I go 250 minus 3x equals 0. 3x equals 250. And then x equals 250 divided by 3. I'll type that into my phone here if I can. 83.3 repeating. All right, this is my x value, which is going to give me the maximum area. Specifically, the question that was asked was, what is the maximum area? So that's not actually this answer. The maximum area is achieved when x equals 83.3 repeating. This area is, how would I do that? Well, up here somewhere I have a formula for a, this in the box there, a in terms of x. So you would actually plug in 83 for x in that formula there. So it's 250 x minus 2/3 x squared, which using that number, 250 times 83.3 minus 2/3 times 83.3 squared. This is the maximum area, whatever that number is. All right, I think that one is more or less reasonable to put on the test, although I don't really like how this number turned out, but I would, if I was going to put this question on the test, I might play around with the numbers a little bit so that you could actually divide this by 3 at the end. But other than that, I think this is a pretty reasonable problem. I hope you feel the same way. Any thoughts about that one or questions? Nope. What else do you want to do? We got plenty of time here, but I ain't gonna hold you if you don't want to talk about anything. That's all right. Somebody says, can we do a related rates problem with an angle in it? All right. We can do that. Related rates with an angle. Trying to think of one that's not too wild and crazy. We'll just try something. These ones are also these ones in the optimizations can be difficult to come up with a question that's not too hard. Okay, how about I have a triangle like this, where this point stays put. The angle is growing. The hypotenuse of the triangle is always 3. All right. So the hypotenuse does not change its length. The hypotenuse is always length 3. But the angle changes, and that will cause the other two sides, they both change their lengths around as the angle increases. Hypotenuse is always length 3, and let's say that the theta increases at a rate of maybe 2 radians per second. All right. I would like to ask, how fast is the vertical side changing when theta is 45 degrees? Let's see if we can do that. Also known as pi over 4 radians, 45 degrees. I think we can handle this. Maybe this might even be too easy. I don't know. So this is a related rates problem. So you should begin by deciding what are the various quantities that are changing, and you should give them some names. So one is obviously the angle there is changing, and I gave it a name. I called it theta already. The other things which are changing, the 3 I said very clearly is not changing, but these two sides are changing as this picture rotates around. All right, this point stays here, the thing rotates around, and then this side, you know, as the angle goes up on this picture, this side will shrink down while this grows a little bit, at least at this point. And then anyway, I'm going to give those two other sides names, maybe of this triangle. I'll call this the base and the height here. And so these are our various quantities which are changing. I think maybe the base will be irrelevant in this question because I'm asking about the vertical side, but it is also changing in this problem. Next, we should write an equation which relates the various quantities to one another. So I want to relate the quantities. The quantities that we care about are the angle, theta, and the h, right? The b, like I said, I don't think is actually relevant, although it is also changing in this problem. I would like an equation which relates the theta and the h. And when you're dealing with angles, usually your equation is going to have like sines, cosines, or tangent in it. And can we relate this angle and h in any way with some of those sine, cosine, or tangent? I think the most convenient one to use would be the sine. The sine of this would be the opposite over the hypotenuse, which is 3. So it would be h over 3. So I'm going to say sine theta equals h over 3. If you use the cosine, you could say the cosine is b over 3, which is that is not wrong, but it's just not addressing the question that's being asked here. It's just about the vertical side. You could use the tangent as h over b. Again, it's not wrong, but it's not going to be helpful to answer this question here. So you should use the sine theta. All right, what about, to solve the related rates question, we first figure out what the changing quantities are, then write an equation which relates these quantities to one another, then take the implicit derivative of that formula. So I should say the implicit derivative on both sides here, impdiff, implicit differentiation. The derivative on the left side of sine is cosine, so I go cos theta times d theta dt equals, and on the right side, h over 3, I think of this as 1/3 h, and then the derivative is 1/3 dh dt. All right. We are on our way now. Then the last step of related rates problem is decide what you need to solve for based on the question, and then plug in for everything else. Now the question in this case is how fast is the vertical side changing? That would be the rate of change for h. That's dh dt. So I'm going to solve for this, and then I have to plug in for everything else. I'm going to plug d theta dt. I said so in the problem that theta increases at 2 radians per second. So that's 2. And here, cosine theta, I'm going to plug in theta equals 45 degrees because I said that's that was given in the question. 45 degrees, which is also known as pi over 4 radians. All right, so when I do all of this plugging in, it says cosine pi over 4 times 2 equals 1/3 dh dt, and dh dt is what I will eventually solve for. What is cosine of pi over 4? That's 45 degrees. I hope you remember your 45, 45, 90 triangle looks like this. And the cosine of that would be the adjacent over the hypotenuse. That's 1 over root 2. So this is 1 over root 2 times 2 equals 1/3 dh dt. Multiply both sides by 3. It says dh dt equals 3 times 2 over root 2. So this is 6 over root 2. That's it. So that means the side on the right is increasing at that rate at the moment that the angle is 45 degrees. 6 over root 2. What else? I hope I did all right with that one. Well, it may be that nobody else has any questions. I guess, the test isn't for another week, so maybe you haven't really started working on this yet. I'll say I'll hang around here for another 20 minutes. If anybody wants to stick around and chat about anything, I would be happy to. Otherwise, I guess I will say goodbye and see you in a week. I think did I mention before, it is time to do the class evaluation survey? I don't know if I mentioned this at the beginning, but I hope that you will take a moment to fill out. This is the evaluation to, you can tell me how you feel the class went. I feel like the class went all right until the last week here. Maybe remember the fonder days when we were all together in person. But yeah, I do appreciate any comments that you have. I put a link to the questions at our class website where the homework assignments are, so check it out. All right, thank you for your attention, maybe. And I'll see you all in a week. Please let me know if you do have questions. I'd be happy to help out by email.